Okay, so no one is waiting at the lobby. Maybe 3 more people, 4 more people are not attending the lecture yet. Now, just for your information, I think the WebEx in USM is a little bit slow. I tried to upload the video, but it takes a lot of time, maybe sometimes 2 days, 3 days before the video is available in WebEx. So if you do not see the online video record uploaded to the e-learning webpage, I hope that you understand that it is because of the slowness in the WebEx. I suppose that you can see my sharing sessions. You can take your attendance. Now, since it's quiet here, I do not listen to any of you or see any of you because you have on your video. So I assume you are to me and is following my lecture. Okay. So we are going to talk about a new topic, part 6.2. Part 6.2, then we are going to talk about something on statistics. So we're going to go to this 6.2, just 6.2. Okay, so this is what I'm going to do today. So today's lecture is a bit challenging. It is a statistical probability distribution function. So what is a statistical probability distribution function? So let me think about it, how to explain it. Now basically, we are going to deal with a lot of special function that has some significance and take on special forms. These are functions that are used usually in the applications of statistics. So what is a distribution? Now, what is distribution? Now, let me explain to you a distributions. If you do experiments, you will have a lot of data. So your data is called X. Say, for example, you take a coin and you throw the coin. So the coin will either be up or down. So you can throw it many, many times and you collect the samples of the result. So if it's up, then you call it, say, X equals to 1. If it's down, then you say X equals to 0, 1 or 0, right? So X is a sample that you collect in an experiment. So X is a variable that could be repeated for many, many times. So when you throw these coins many, many times, you will end up collecting a lot of data. Right? So this data, each of these data is called X. So some X will be just 1 or 0, 1 or 0. Then you count the numbers of results where X is 1, and then you count the result where the X is 0. So then you can then plot the probability of how many times out of these experiments the coin end up to be 0, and what are the probability that the coin end up to be 1, right? So a graph that is showing the probability versus the results. In this case, there are only two results, discrete results. That is either the result is 0 or it's 1. So this is called a discrete distribution, right? So you always carry out an experiment, and then you measure the result of experiments. In this case, the result is either X is either 0 or 1. Then you repeat it many times. Then you count numbers of times when X equals to 0 occurs. and then you count how many times the result 1 occurs. Then you can take the ratio of the time when result X occurred to the total numbers of times. For example, you throw 100 times and you find that, say, 44 times X is 0. So that means the probability of X equals to 0 is 44%. Right? Then the probability for X equals to 0 would be like 40%. Then you can also calculate the probability of the head, or say X equals to 1 to be the numbers of X equals to 1 occurred divided by total numbers of time you throw the coin. So basically in statistics, this is what you do, right? You collect a lot of data. So the data is a number, and we usually use X to denote the result of the collections. So the result is either yes or no, 0 or 1. Sometimes you could have more than one result. Say, for example, you want to say say how many people are wearing say red color shirts, how many are wearing green color shirts, how many are wearing say white color shirts. So wearing green color, yellow color, or whatever color, it can also be an X, which is an experiment that you can measure. So the important point is that you have to define what are the quantity X you want to measure, and then you measure it many times. Then you count how many times or a particular X occurs. Then you plot the probability as a function of the X. Then you got this what we call a probability distribution. So there are two types of distributions that is discrete, or probability distribution that is continuous. Okay, I suppose that most of you has gone through maybe your Form 5 or your Form 6 or the matriculation. So in these courses, you will have already studied statistics. Okay, so I suppose that the distribution and revisions of your statistics. Okay, so so every statistics, it could have its own distribution. So the simplest distribution is what we call a Bernoulli distribution, where you could have only two possible outcomes in your variables. X is equal to 0 or 1. For each X, you have a function P describes the distribution of how the probability would have. So it seems there are only two values for P. So the P depends on your X, and X is either 0 or 1. So there are only two values for your P. In this case, the first P is here is 70% for X equals to 1. And the P, there's a probability for X equals to 1 is, say, in this case, it's just 30%. Okay. So this is a very simple case where there's only two output for your X. You could also have situations where you could have more than one possible X. So the X could be not only 0 or 1, but could be, say, numbers. Okay, so for example, I think, say, okay, maybe you carry on an experiment. So carry experiments of calculating, you go and do experiments, you go and survey your friends, say, go and survey 100 of your friends, and then you count the numbers of your friend who would say play games, right, on your handphone. So the numbers of games, well, the number of times your friend will play games in a day. Some of your friends play games on a handphone, say 10 times. Some of your friends will play 9 times. Some of your friends don't play any games on your handphone. So you can go and collect all these numbers. So in this case, the particular friend of you may end up playing, say, 10 times the games on handphone, or maybe play no games at all. So you can go and collect all these samples, then you can plot another probability distribution as well. So in this case, the probability distribution will be different from the Bernoulli distribution. Bernoulli distribution allows only the result of your X is either 0 or 1. So in this particular experiment, the result of X could be discrete. It could be start from 0 or 1 or 2 up to some infinite integer numbers. So you can also collect the statistics. Then you can plot the probability of your friends who play games or who don't play games at discrete times per day. Then this will form another probability distributions. Okay, so in this particular case, the X, which is the data that you collect, forms discrete points, and the height of the y-axis is the probability. Okay, so there are probability. This is called a binomial probability, where their points could be described by a function. So this is what we call a distribution function, probability distribution function. So if the probability of these experiments follow binomial distribution, then it has this formula. So in this formula, X is a variable that describes the data, and then the values of P would describe the probability where X would occur. Okay, so for example, the probability it will be highest when X is 20. In this particular example, the red color one. Maybe if it's a green color one, then for this green color one, the probability will be highest when X is somewhere, say, 14 or so. Okay, so a probability distribution function is a function that depends on an independent variable X, right? So this independent variable X is the result. So usually in this sample, you have many different values of X. So here in this particular case, well, there are many different values of X. And each of the distribution function in the statistics could be described by this particular form of functions. Now, what is important is this, you should understand that in a statistical sample, this statistical sample could follow a particular statistical distribution. The statistical distribution is nothing but just an functions, right? So for discrete distribution, we have Bernoulli distribution. We could have binomial distribution. We could also have a uniform distribution, right? That looks like this. That is, all the chances of any particular event to happen is the same. Okay, so this is called a uniform distribution. So uniform distribution is very simple. It's just a constant for all values of X. We also have a Poisson distribution that looks like this. So so you go and collect X, where X is allowed only to take on discrete values. Then the formula that describes a Poisson distribution is this, right? So the X is a variable that a particular X will happen is given by this formula: exponents minus lambda times lambda power X divided by X factorial. Okay. You could also have a continuous distribution. In the continuous distribution, which is the values of the data, in principle, could take on not only discrete value, but continuous value. So you should understand that you have in principle either discrete points or discrete values or continuous value. Okay. So for example, if you go and say the height of the friends in populations, then the height, which is the number you measure called X, could vary from say maybe 1.0 meter up to say 2.0 meter. So between 1.2 or 1.0 to up to 2.0, all possible height are possible, right? So this is an example where X is a continuous variable. So the very common distribution function for a continuous variable is the normal distribution function, right? So normal distribution function takes on this particular form where X is a variable and you have sigma and mu. Now, the other example of a continuous statistical distribution is what we call chi-square distribution. It's a very complicated function of X where it's expressed in terms of gamma. where gamma is called a gamma function. It's a kind of a special function which depend on the values of k. Okay, so when k changes, then the gamma changes. And how this gamma looks like? I think the gamma looks something like this. Right? So this x-axis is the gamma value, and this is a k value, and this is called the gamma. I think gamma is called, well, k is a variable in the gamma function. So this gamma function is taking in values of k, which is discrete. K is a variable, k is a constant. So if k is 1, then the gamma takes on some number. When k, when k is, where is it? Okay. K is 1, then gamma of half takes on some number. When k is 2, then gamma of 1 takes on some number. So the values of gamma depend on its argument. Okay, so this is a gamma function, and this is its argument. So when k is 1, k is 2, then you can actually calculate. But for k which is not discrete, gamma function also can be calculated. Okay, so this is the form of the gamma function and how it looks. Now, gamma function is very common in physics. I purposely bring in this gamma function here and introduce to you because for those who are going to study physics, theoretical physics in, say, statistical mechanics, you will see the gamma function later on. Maybe when you do quantum mechanics later, you also see gamma function. So gamma function is a kind of such function that you will encounter if you do theoretical physics, or it appears in your second year, third year, or fourth year. Okay. So anyway, the gamma function is just a number. It depends on the k. So the distribution function for normal distribution is taking this particular form. So we also have other chi-square distribution function. This is what I mentioned, chi-square distribution function. The variables is k, and the chi-square have this particular shape. And the chi-square distribution depends on the values of k. So when k equals to 1, then the chi-square distribution looks something like this. When k equals to 2, then it looks something like this. When k equals to 3, then it starts to have a bump. Then when k equals to 4, it's starting to have a bump. So this is a chi-square distribution. It looks like a very special function. You can also have an exponential distribution function that looks like this, and then it looks like this. Now, okay, the last example is the student's t distribution. So the student t distribution looks something like this, and it is also dependent. The values of it also depend very much on the gamma. Okay, so the gamma depends. The gamma functions is a number. Depend on what is the mu here. Right? So the mu could be any real number. So you slot in any real number, then you get the values of gamma. Then the function of p depends on the variable x, which is raised to the power of minus norm mu plus 1/2. So if you plot these functions, p as a function of x, then different mu will give you different functions. So we call this a family of curve, where each curve is labeled by different mu. Now, I hope that you are not confused. I'm showing you a collections of special function. Right? So the special function in this particular case is the Bernoulli distribution function, and is a special function called binomial distribution function. This is a special function which is just a constant, and this is a special function called the Poisson distribution function. Now, remind you that each of these special function is characterized by what we call the shape parameter. Okay, shape parameter means that it is a set of parameters characterize a particular function. Now, for example, now in this binomial function, the shape parameter, right, depends on n and p. So n and p are two sort of like independent parameter. The n can take on any discrete number, and p can take on any continuous number lying between 0 and 1. So when you change the values of P and when you change values of N, then you got different function, right? So each of the binomial distribution function depend on the label, well, not the label, depend on the shape parameters. And in this particular case of binomial distribution, two shape parameters, N and P, but N is adjusted to some number, P is adjusted to number, then the function would appear differently. So each of the distribution function not only has the form of the function, it also has the shape parameters. And you need to know the shape parameter for a particular binomial function. For example, binomial function, it has two shape parameters, N and P, and N only takes on integers, positive integer, including 0, and P is the another shape parameter, takes on between 0 and 1. So X is just the normal data variable. Okay. This particular example of the uniform distribution. Now, what is the shape parameter? What is the shape parameter for the PDF for this uniform distribution function? Now, PDF stands for probability density function. It's just a function for this distribution. Now, the shape parameter for this uniform probability is just P, right? So the P can take on any number. So it's just take on between 0 and 1. Okay, so this is called the so for the uniform distribution function, the shape parameter is just 1, and then this is P. For this particular Poisson distribution, parameter is just lambda. So when you adjust the lambda, say from 5 to 15, then you can now see that the probability distribution function PDF or the Poisson distribution function will look differently. When you have a PDF or probability distribution function, you have to know what is its shape parameter, and then when you adjust the shape parameter, then this probability would be different. Okay. For normal distribution, the normal distribution is the most important distribution that you need to know, because in nature or in experiments, most of the experimental sample that you would have collected would normally form a normal distribution. You know, normal distribution also has a different name. They call it the bell-shaped distribution. Sometimes it's also called, I think it's also called the Gaussian distribution. Okay, so either Gaussian distribution or normal distribution, or sometimes you call it bell distribution. It's all referring to a function, distribution function that looks like this. So for the normal distribution function, P has two shape parameters. The shape parameter here is the sigma and mu. Basically refers to the values of the spread in a function, right? And then mu refers to the mean of the function. Now, usually the mean here, mu is the mean. It is referring to the highest peak. So for example, you look at this green color shape. So this green color shape has a mu equals to -2 and sigma square equals to 0.5. So mu -2 means that the peak is happening at -2, and sigma square 2.5 refers to the fact that the width of this is 0.5 square root. Right? The sigma here is a measure of spread in the Gaussian width. So sometimes, so for example, you take the highest point, then you take the half of the highest point, then you measure this width. Usually this width that is at the middle give you a rough idea of how wide the shape of the Gaussian is, and it's usually given by sigma. So in this case, the sigma is square root of 0.5. If you compare the sigma of the green color and the blue color, so the blue color has sigma of 0.2, whereas the green color has 0.5. Right, so it means that the sigma, which is the spread for the green color curve, is larger than the spread in the blue spread. Whereas for this, I think it's a yellow color. For this yellow color, maybe not yellow color, this is a brown color, orangish color. So this is a sigma square equals to 5.0, which means that the spread is the largest as compared to the other colors. And this orange color curve is located around the center of mu equals to 0. So the normal distribution function is fully characterized by the sigma, and know what is the sigma and mu, then you would know the shape of the distribution function. Okay, so you need to know these are the normal distribution function. You also have this chi-square distribution function. So chi-square distribution function has only one shape parameter, which is a k. But in this case, the k is not continuous but discrete number. Right? So if you compare the normal distribution function and the chi-square distribution function, normal distribution function has the parameters sigma and mu that is continuous. Whereas in the chi-square distribution, the k is not continuous but a constant. Okay, well, a discrete, positive discrete number. For the exponential distribution function, the shape parameter is lambda. Lambda is a continuous as well. For the student's t distribution, the shape parameter is mu, and mu is also continuous. So I give you a special function, Poisson distribution or uniform distribution, then you know how this function looks like. So one of the agenda in today's lecture is to learn how to use Python to generate this function. The brute force method to do this is to say, give you this function, then you just print out the shape of this function called Bernoulli distribution. So for example, you can write a code to calculate p equals to p squared, blah, blah, blah. You just print out these functions. And then you just set p to be 0 and 1. Now you can also write your own code to calculate the values of the binomial distribution for values of x that is discrete. Then you calculate what are the values of the probability for different values of x given by this. So you can adjust your p, then you get the binomial distribution. So I think that would not be difficult. So if, for example, I ask, okay, now this is the binomial distribution, okay, and then please generate for me, say, this blue dot. Now, can you do that? Now, it is quite easy to do that. You can do it if you have this formula. But there are some functions which is quite complicated. For example, this normal distribution function. Now, for this normal distribution function, can you write a code to generate the shape of this? I think you can. If I'm not mistaken, one of your early assignments, that is why I asked you to do. I give you a function that looks like Gaussian and ask you to generate the function. Then you just plot the functions based on the formula. Okay. But in statistics, these few examples of distribution function is very common, right? This common distribution function. So a statistical sample usually belongs to one of these distribution. So if it's not normal distribution, it will be chi-square or it will be exponential or whatever. So PDF in statistics is very common, so it is always used, right? People encounter this distribution function very often and use it. So it so happened that in Python, they automatically define this function in their package. So if you, for example, want to generate the student's distribution function, you do not need to write your own function based on the formula and then generate this function for yourself. You don't need to. You can actually ask the Python to help you to generate this code without defining the function. Right? So this is what we see. Okay. Now, for example, we are going to learn how to use the Python to generate these few special functions. Maybe the first example would be, ask the Python to generate for us the gamma function. Now, gamma function is a special function that has defined to be a function which is depending on the values of gamma. So it is actually defined in terms of integration. So for any x which is positive, you take t raised to the power of x minus 1, you multiply by e raised to the power of minus t, then you integrate t from 0 to infinity. So it looks like a very complicated thing. You can't really do it analytically. I think you can't integrate the t variables in the definition analytically. It's just very similar to the log. Remember the natural log. In your natural log, you define natural log as 1 over t, and then you integrate dt from say 1 to some x number. So the gamma function is also similarly defined in the similar manner as the log function. Is defined as an integration. So integrate over all t from 0 to infinity. So all t values is what we call integrated over, and the values of the integration function depend on what you put in. So you can do it very easily, but people work out that actually this gamma function has some very interesting properties. For example, they obey these what we call recurrent relationships. Gamma evaluated at x plus 1 is just equals to the x times gamma evaluated at x. For example, if you know what is x equals to 1, then you can calculate x at 2, right? Because x at 2 is just equals to 1 times gamma at 1. And the values of gamma at 1 turns out to be just 1, okay? Now, we can also prove that the gamma values evaluated at half is just a square root of pi. So using these very simple recurrent relationships, then you can actually calculate the values of gamma for any n is equals to n minus 1 factorial, right? So the gamma is a special function which is very important and very often seen. So if you want to generate the gamma function, and for example, you want to know what is gamma of say x equals to say 2.2, the values of gamma when x equals to 3.5. Now, how do you do it? So it turns out to be quite difficult. If you want to, you can try to, maybe later on, we can try to write our own integration functions to calculate the values by carrying out this integration. But it turns out that in Python, there's one package called math. I think we have seen math before. So in the math, you can actually generate this gamma function, right? So so this is an example. So I'm not going to do this for to display this in detail. It so happens that if you want to get the gamma function, what you need is just call out the gamma, right? So the math gamma would give you, well, the math gamma would be able to call out the values of the function. So maybe just a short one, maybe it should be okay. I'll try to show you how you can call out the gamma. So what you do is you import the math, and if you want to know what is the values of gamma, so you say gamma, well, I think it's called math dot gamma, then you set math of gamma at 1. So by doing that, you'll be able to generate or calculate the values of the gamma function. And what happens if I press the button? Expect the values to be 1. Yes, this is 1. Now, if I press gamma at half, then what you get the square root of. So this is very much square root of pi, pi over 2. Maybe let me do like this. So this will also give me a values of math pi divided by 2. So let me print out this as well. Let me print out both, just to make sure that I see two numbers, and these two numbers should be the same. Pi is not, should not be pi, but math of pi, math of square root of pi, sorry, this would be a square root of pi, square root of pi, 0.5. Okay, so this would means I am calculating the values of pi raised to the square root, and both should give me the same number, right? So obviously, you can calculate the gamma function quite easily from the math. If you want to plot, say, for example, the function of gamma, that is how you can plot it. So first of all, you decide that your x is a range. Well, so in this case, you need to import numpy as NP. Then you use a range from, say, 0. No, yes, is gamma defined for x. No, gamma is not defined for x equals to 0, but has to be larger. So you have to start the gamma x from, say, 0.01 up to some number. So in this case, let's reproduce this graph. Say this is 4.0. 4.0, and at the interval of, say, 0.05. Okay, so that will give me a range of x. Then what I do is that I want to plot the values of y. Now, y should then be a values of next dot gamma for x. Right, so that will give me a values of x. Did I get the values of x correctly like this? No, there's an error. So of course not, because the x that goes into gamma to be a number, but not an array. Right? So here the x is that we have to generate the values of x, which is an array. So I said, yep. X. Now, any questions? You can raise your hand, or you can talk to me, please. So what I'm going to do is that x is a range. So I'm going to generate the math of gamma for x in x. Well, this is not x. It's called, say, dummy. Dummy. So we have been used for many times. So we have been using this for generate an array by letting the dummy to go through all the values in x. So that's how I get this number. This is the values of y, and this is the values of x. So this is my y like this. Then I can then plot. I need to use import from pilot import everything. Right. So this is usually the way how we do it. Then we use x and y, and then like this. So this is can be used to plot the functions. It looks like this. But let us try to do something which I have not really done much. So it so happened that sometimes we want to use not PyLab. We need to use what we call matplotlib. Matplotlib is a very important library that would be used for plotting. Graph. Which is matplotlib. So we're going to import from. We're going to import a library, pyplot. So let us try to use matplotlib to plot the graph for us instead of using the plot. Now this plot, when we use a plot, the plot is actually coming from PyLab. Okay, so there are two ways to do the plot. Either you use PyLab, so for example, from PyLab import everything. Then by doing this PyLab, yeah, by PyLab. Let me see, I forget PyLab. Yeah. So in order to plot the graph, you can use either PyLab and then you use plot, or the other way to do it is not to use the PyLab, but we use pyplot. Pyplot from plotline. It also allows us to plot, but the syntax is slightly different. So today I'm going to use matplotlib to do our plotting instead of using the plot from PyLab. So I will import this and then I'll call a shortcut name called PLT. So the PLT is just a shortcut name which refers to matplotlib pyplot. Right? So instead of typing matplotlib as a full name for pyplot, I just type plt. Right? So in order to plot plt, what I need is I need to say plt dot. Now in the plt, let me see plt help plt import. So help file. So the plt, which is the matplotlib.pyplot package, you can check out the help file on this. So a lot of things that you can read for yourself. But what we want is usually we want to use pyplot. Sorry, we want to use plot function. Matplot contain many packages. One of the package, and inside the pyplot, there's a function called plot. Okay? So this plot function, plot, the function which is used to plot graph, will be inside matplotlib. Okay, so we are going to plot the x and y using the plot function, which is found inside the matplotlib pyplot. So how I do it? So it's the same thing. So that's it. Okay, so that's how you plot the special functions in the Python. Now, other than gamma functions, there are also a lot of other functions. For example, beta function. For example, I think the Bernoulli function. For example, now you see a lot of special function when you study quantum mechanics. There's another function called Lagrange function. Functions. So you encounter many special functions later on. So if you have come into my class in ZCE 341, you have at least some exposure to these special functions. So different special function has different forms and has a different form parameters. So if you want to plot, say, for example, another function called error function or gamma function or beta function, you can use the package in math to get you the values and plot the function. Okay, so this is just a demonstration. Now, what we're going to do now is to try to generate the probability distribution function for some special function we are interested in. For example, let us try to plot the PDF, that is the probability distribution function for the binomial function, as well as the probability distribution function for the Gaussian distribution. Now, you remember the Gaussian distribution function looks quite complicated. It is this. Right? If you want to plot this function, you don't really need to define this function. It will be actually quite lengthy if you want to define it, but it's okay. You can define it. If you want to say plot the binomial function, no, not like that. Poisson function. You can also try to print it out as well. So in this example, we are going to see how you plot the, for example, of this special the binomial function as well as the norm distribution function. Now, in order to do that, this is the command. The command is this, to use SciSpy. Now, the SciSpy, as I mentioned earlier on, is the collections of packages that function that is useful for mathematics as well as physics. For example, it contains many definitions for the special functions and also the probability distribution functions. So for those very common distribution function, or for those very common probability distribution function, you can find them in the SciSpy. So the trick is you just have to import the in SciSpy, you have many packages. One package that is useful for doing statistics is the SciSpy.stas. Right? So you can find the all the common distribution functions in statistics within sciencespy.ss. Now, before I proceed on, I just want to mention one thing. Now, all these distribution functions that I shown you here, I'll call this in general PDF function. But for some reason that I cannot explain why, some of the distribution function is not called PDF. They call it PMF. Now, PDF stands for probability distribution function, whereas PMF is probability mass function. Right? So either whether it is a probability mass function or probability distribution function PDF, it all refers to just the formula of the distribution. Now, it so happened that in the sciencespy function, in the sciencespy stats package, sometimes you have to use PMF, sometimes you have to use the word PDF. So let us learn a little bit how to call this function. It's quite simple. It's not very complicated. It's just a syntax, right? So once you learn how to use the syntax of calling the distribution function, then it will be quite simple. Now, this is the syntax. So first of all, you need to know what is the name of the distribution function, and then you need to know what are the arguments of the distribution function. So if you want to, let's say, for example, you want to plot, say, the Gaussian function. So you need to know what is the name of this Gaussian function. Of the Gaussian function is called normal distribution function. Okay, so the normal distribution function has a name called NORM. So in sciencespy, the distribution functions for normal is called NORM. Now you have to find out yourself sometimes what are the names that is called. Maybe I just show you an example. This is what I did. So you go to I will go to Google. You just say what do you call normal distribution function in sciencespy stats. I think. Then now this is what it says. So the sciencespy statistical functions. So the normal distribution function in Python, specifically in the sciencespy stats package, the name of the normal distribution function is called NORM. Right? If you are looking for, say, for example, the distribution function for Poisson, right? So you can try to find again the name of the Poisson distribution function inside, right? So you call it Poisson, P-O-I-I-S-O-N. We call Poisson. It's a French pronunciation. So this is how you find the Poisson distribution function in the internet. So the Poisson distribution function in sciencespy is called Poisson. Okay. So in order to generate the functions of either Poisson distribution function or normal distribution function, you need to know the name distribution function, of course, and you also need to specify the parameters if you want to generate the function. Okay, so in this particular example, let's try to generate the, in this case, let's just try to generate the Poisson distribution function. The Poisson, the binomial. So in the Poisson, in this case, binomial. Generate the binomial distribution function. Ask the Google what is the name for the binomial. So you say the binomial. So the binomial distribution function in sciencespy is called BIOM. Okay, so this is a sciencespy. Let's try to use do this sciencespy binomial function. The PDF for us. So the way how we do it is very simple, right? So you just have to call out the PDF. Now for the binomial PDF, it emits first the values of x you want to plot. So you have to tell where is the x. You want to plot from say 1 to 5, or to know from what number to what number. And then you also have to know that for this particular binomial functions, it has two shape parameter. So you have to specify the shape parameter. If you want to say generate normal distribution functions, then you have to know what is the name of it, which is called NOR. So for this norm, you need to supply the two parameters, because the normal distribution function emits two emits two parameters. So it's very simple. Let us try to see if I can do it fast enough. So first of all, you just have to import this. Okay. So we import this SciSpy SSS. So this SS is a shortcut for that. So according to the explanation here, if you want to say import binomial function, okay, SS, which is SciSpy stats, you take binomial function, and then what you want is that in the binomial function, it has many other functions as well, but what we want is to plot the potential, the probability distribution functions of x, where we're going to vary from one number to another number, and then we have to specify the n and p. So what are the n you want to specify, and what are the p that you want to specify? But in order to assign the correct n and correct p, you have to go back to the definition for the binomial distribution function. So for the binomial distribution function, the values of p is between 0 and 1, whereas n is. Okay, so let us try to generate, for example, the green color one. So the green color one has p equals to 0.7. Maybe not very difficult to see the green color. Let us generate the red dot color, which has p equals to 0.5 and n equals to 40. So let us try to generate this curve for the x, which is ranging from 0 to 40. So we are going to have this running from 0 to 40, and we're going to make p 0.5 and n equal to 40 in our code. So first of all, let us define our n. N is 40, and then the p is 0.5. Okay. And what is your x? X is in the range of NP. Well, range would do, starting from 0 up to 40. Let us make it 41. 41 means from 0 to 40. So X is an array that contains 40 numbers. Then by doing that, this will, SS binom PDF, will then take in the values of X, and then it gives us values of n, which is 40. So we call this 1. Now when I press the button, it would be evaluated for all these 40 numbers. So let's see it works. Press the button, you got an error. So binom has no attribute of PDF. So I have run into trouble. Let me check. So it is not called PDF. For some reason, now binomial is a discrete distribution. So I say for this distribution is not called called probability distribution function, but it's called probability mass function. So you have to use because binomial is a discrete distribution. Now when we want to generate distribution function, we call this argument PDF. Prefer the reserve for continuous distribution, whereas PMF is reserved for a discrete distribution. I reserve on that statement. So that is so that means means that have been able to generate the X and Y. Now, I'm going to so again, I'm going to import import matplotlib. I plot my plot as BLT, and I'm going to plot plot BLT to plot X and Y, and then I'm going to plot it on a discrete point. Okay, that's how it is. So that is how is it like. So it looks like this is just the values of, well, this is just a potential of the PDF for the binomial function, which has 40 and at p equals to 0.6, maybe 0.5 is what we want. Okay, so this is 0. So remember, this is very similar to this, isn't it? So this is the function we try to reproduce, which is the red color one. So it's centered around 20, and then its peak is around 0.1, between 0.1 and 0.15, maybe 0.1 something, 0.12 for n equals to 40 and p 0.5. So this is a peak which is around 0.1 something. So we can try to ask if this compare with what, see this, which is 0.12, right? This is a peak value, which is roughly what we have seen. Right? This is 0.12 something. So if you want exactly what is the values of this point, maybe you can ask the code for you. So maybe you can just say this, print the values of the binomial distribution when x is equals to 20. Right? So it's 20, then the answer is 0.125. So this should be 0.125. B corresponds to this number. 0.125 is the peak. So what I'm trying to show you is that this is how you generate the distribution function for binomial function by specifying the two values of the parameter that characterize the binomial function. Okay, so if you want to say, for example, generate a binomial function which has a parameter of say 10, something like that, with a p which is say 0.1, then you press a button, and this is what you get. It looks like this. Okay. This distribution function generated by calling the scipy.stats package, and inside the scipy.stats package, you have many different distribution function. So you need to know the name of the distribution function. Then after you have called the distribution function, decide what you want from it. So in this case, we want the probability mass function of the binomial. That's how we. So let's try then to plot the PDF for the normal distribution function. So in that case, so this will not be called normal, not be called binom, it will call normal. It's called, I think it's called norm, stand for normal. And since it's a continuous function, I think it's called PDF. Then you have to specify the variable x and also sigma and mu. Now in the of the normal distribution functions, you need to know what are the argument to put in, right? So argument here, ARGS, has two numbers. So I think here the FRGS, the argument that should be to this is the values of, let's see, I just want to show you how you find out what is this. Gaussian real number. No, it isn't specified here. Let's see. It's not specified here, but anyway, the norm or the norm distribution emits two arguments. And the argument should be the first argument should be the mu, and then the second argument should be the sigma, right? And then sigma or mu sigma. Okay, I forgot exactly, but I have make a literature review. I have found that not the sigma and mu. Yeah, I think this is how you do it. Mu and then sigma. Let's come back to our book here. Now, in order to generate the distribution function or Gaussian distribution, you have to provide sigma and mu. Right, the values of the sigma and mu. Now, let me check again. I keep on forgetting. The is mu and sigma. So you have to the mu and the sigma. Now, in case you do not follow, let us come again to the Gaussian. A Gaussian distribution, normal distribution function has two input parameters, mu and sigma. Now, mu is the location of the peak, which is also the average, right? So it's the mean of the distribution, whereas the sigma refers to the spread, right? So in order to get this function generated, you have to tell the Python what is the values of your mu and sigma. You have to tell it by, you have to tell the sigma, the mu first, only then you tell the sigma, because this is the syntax. Okay, so provide the values of mu parameters for is mu. It's easier, and then the sigma, say equals to 1. Right? So this would easily give you a width of 1. Gaussian curve, a Gaussian curve or normal curve has a width, and the width is a sigma. So sigma is the length scale in a Gaussian. The larger the sigma is, the shorter is the Gaussian. So if you want to display the whole, then you better start from the left hand side of the peak and the right hand peak. X1 on the left and X1. Now, X1 on the left be a few sigma from the right? And then the X2, where you want to plot the function, should be a few sigma away, maybe 3 sigma away from the right. So this location at the center is X equals to mu. I mentioned just now, mu in a Gaussian is referring to the location where the peak occurs. So is X equals to mu. So we want to plot the gamma, the Gaussian function, from say 3 sigma away, the left of mu, and 3 sigma away from the right. So this is about 1 sigma, right? So by doing that, you'll be always able to display the Gaussian function as a whole. So if you just simply plot the Gaussian function, random x, and sometimes maybe you wouldn't get your x to be displaying very nicely. So this, anyway, plot this. It doesn't look like Gaussian function, but it's like you expect. The reason is because the range of the x you display the Gaussian function is not correctly done. The correct way to do it is like this. So you want to generate the sigma for x1. Now x1 should be on the left side of mu. Mu is on, then the left hand side of mu should be x mu minus say 3 times sigma. Right? This is referring to the location x, which is 3 sigma from mu. Now on the right hand side, you also want to make this to be say mu, say plus 3 sigma, right? So then your range should be from x1, x2. And instead of using range, maybe let us use inside in space, right? In space, maybe you put maybe 40 points. To use a lean space, you need to import numpy import as np, and then this would be np. So this would generate a range of x from x1 to x2, and there are 50 points between x1, x2, and x3. Yeah, that's how it looks like. So it's much more robust in this way to x range. Now, if you simply do from say 1 to 5, then you would not what to call cover all the features of the Gaussian function. So at this point of time, we have learned a new syntax, which is the scipy.stats package. And then you call out the particular distribution function name. Then you ask the mathematical Python to give you the values of the distribution function, which is defined based on the formula that is specified here. So you do not need to type in this formula. It's already contained in the scipy.stats formula. But when you call a particular distribution function, you need to know what are the parameters. Then you have to supply the parameters in the correct location. So if you specify, for example, p in opposite directions, say, for example, if you say is n for p, so you put p first and n first. Here, if you put me and sigma in the opposite, then you trouble. Okay, so you have to be careful when you use when you specify the parameters. Right? The way how you do the parameters, you have to check on the size spike. So that's how we do it. So at this point, I think we have done with this. We have done with this distribution function, how you generate it. So this is how I generate a number function for discrete numbers of n equals to 8. And this is just a fancy thing of writing a V lines. The V lines that I do here is just a way to join the point to the line. Okay, so the binomial function has also been generated just now. Okay, I think it's getting too late for you. Maybe we take a break. But before we take a break, utilize what we have done. So we have just use the scipy dot generate distribution function. But later on, we are going to do something which is more complicated. Right? Other than just using the PDF or PMF, like this one, to generate the function, we want to use another form, another function in the scipy. That is, we are going to generate sample data. Instead of generating the function, we're going to follow a particular distribution. So we'll come back at 4:20, 4:11 now, maybe 4:16. We'll come back at 4:16. Okay. And then we come back after 5 more minutes later. Okay. Another question, ask me, okay? Take a break now. randomly. Right? So these are all the numbers. Now, if you were to do a binning on this data, now what do you think the distribution of the? Now, let me say what you mean by binning is that you can try to now see this data is generated using the function random. So you try to bin this. Now, what you mean by binning is this, right? So say you have many x. There are here, say 100x, or maybe 1,000x that is then generated. So here is 1,000x that is being generated. So what you do is that you try to the values between into say the try to separate say the x between 0 and 1 into 20 subintervals and has a width of delta x. So if you times 20 times times 20 times, which is the times number of beans, then spend the whole x from 0 to 1. And then you have to count the number of x that lie in a bin. Then you'll be able to obtain and distribution for this sample set. I think I have a picture to show you. So now, for example, if I generate 100, now this cross along this x-axis represents say 100 different values of x that is generated. So the left hand side here, x min should be 0, and then here would be maximum values of x. If the x data is generated using the random, then this last number x max should be 1, right? So partition between x min and x max into NP partition. So into NB partition. So you have 1, 2, 3, 4, 5, 6, 7. So in this case, you have 9 partition, and each partition has a width of delta x. Right? So delta x is very easy calculated. So the delta x and numbers of partitions can be easily be viewed in this manner. So if you have partition and then you start counting, right? So you can count how many x are lying with inside this bin. Then say for example there are 10. So that means like bin is, so then you plot this number as that. Now then you count the numbers of x lies with x bin. Then you plot numbers of x that lies in the bin. So within each bins, there are a few x that's lying there. So I write here, say for example, if there's value of x, this dot here, is lying between x I minus 1 and xi. So the bin I has on the left the values of x as x1. On the right of the bin, no, the right hand side edge of bin I is xi. So you can count how many x are there within this bin. I just know what a binning. Given the numbers, you do the binning. Tell what is the numbers of bin, right? So then you take the smallest numbers of x, then you do the counting. Then once you count the numbers of x in the bin, then you divide of count in the bin by NP 100x. So of x, so you count the numbers of x in a particular bin, then you divide it by 100. And this y-axis will represent because the numbers of x in a particular bin will always be less than the total numbers of x along the x-axis. So this is a percentage. Right? So this percentage is maximum equals to 1, but it usually is much lesser than 1. So we call this a normalized probability. So this y represent the numbers of waiting for people to. So so this is how. So if I ask you to write to do this spinning, it will be quite quite difficult task. So here, now many numbers of data. I want to bin it into say 20 bins. What kind of distribution do you think you get? Right. Now, the most likely, the answer for the question is that if you the random sample that's generated using random, most likely you get this, right? So you will get this kind of distribution. That is for values of x within a bin, to find x in a particular bin would go the same, right? For example, the chance to generate or to find an x which is say 0.3, and the probability to find an x which is say at 0.9, and the chance to find an x at 0.01 would be almost equal. Okay, so let's see if you can bin this data. So you have many data. Not sure if you want to bin this. So if you want to bin, you have to write code. Now, in principle, I want to have the admin come in. So a procedure to do the binning is quite involved. So you have to first find the minimum of the x in the data and the maximum of the data. Then you have to scan the first bin. Now the first bin, then you have to count in the number, which is like so you have to count one by one. After you have all the values of x in the data between 0.1 and 0.2. Right, so 0.1 and 0.2 is the second bin. Then you have to do the counting. So to write a code to do all this counting, it could be quite difficult. However, it is possible to do the binning by this program sample data. So let me try to show you how to do that. So this is now it is possible to bin the data into histogram by using this function PLT. Copy this PLT inside this I.PLT, it has a function called histogram. So maybe I'll do this first. Okay, some histogram. Yeah. So histogram is a function which is included in the matplotlib. So in order to do that, you just have to provide the data x, and then you have to specify the numbers of bins you want to do. Then it will be able to do the binning for you. And also, let's try this. This is how you do it. You just which is the matplotlib plot. Then you call out the histogram function, then you provide the data. So the data has this name, and you do it into 20 bins. You have to specify density equals true. When you see density equals true, what you get is the normalized function. If you say density equals to true, or you say density is false, then what you get is the count instead of number of count divided by the total numbers of point. In this case, the point is 100. So this is what you get. So you see that the distribution function for this 100 random number, which is obtained from the random number, is not really distributed. As I said, it should be. There's something wrong with this. I don't know what happened. So it looks like this is not normalized correctly. Since the density is true, but the y-axis is larger than 1. So I'm confused. Let me check again. It should be true. It should be normalized. So let's see what is. I'm trying to do it again. So there's a beans, plot a histogram. So I'm looking at this density. So the density, so density should be true. Okay. So it will, if I set density equals to true, then it will return the normalized count from the probability density. So that is what I expect. The command is histogram x bins equals to the numbers, and then density equals to yes. So I should say this to be yes. Well, true. True. Already set to true. If it says, yeah, I think it's true. Maybe I should have this. Sure. Now, thing that I don't know how to fix this. So this is not what I expect. I expect the density, if it's fixed, to be true. Someone is saying something. The screen is moving too slow because of the lag problem. Lag. Let's see if it's still lagging now. Is it lagging now? Let me try to scroll this. I try to scroll this up and down. See. Anyone find the screen is still lagging? You can't see. It seems there is trouble. Still lagging. So we have to be a little bit patient. The line is indeed very bad. Anyway, let me raining outside. It's not raining from my point. My house here is not raining, but maybe it's the line that is slow. Now, okay, if you have problem, to my screen as much as you can. Later on, I will upload the record online. Then you can try to read back or refer back to the code. Okay. Okay. When I set the plot histogram data bins, I expect the axis to be normalized. Okay, but it looks like it's not. to fix this. Probably I cannot fix it. I do not know why is that like that. Less than, should be less than. Now this is what we are doing. We are trying to generate the data, random data, 100, and try to put the bins, 20 bins of that. Okay, random is not defined. So I should call import as MP, and this is MP. Random. Okay, so now I have problem with random. I sometimes have this problem, okay? Random. Why is that the random is not defined? Can anyone help me? Random or maths.random. Okay, maybe math import. Maybe random maths function, no. Random. Random. Now I got stuck here. I do not know why is that my random doesn't work. Work. I should import random. Let me try random. Is not defined. Okay, I don't know what happened. Let me say random in Python. The syntax to use random, which we use very often, but for some reason it doesn't work. Python random. So import random. So import random. Import random. Now, by doing that, I'll be able to generate random. Yeah, let's try it again. Import. I hope this gives me the correct number. I still have problem. Random. I'm stuck. Try again. So anyone can help me? Why my random doesn't work? MP random doesn't work. Random. Okay. np.random. Okay, so that should be np.random. np.random.normal. Thank you. Thank you very much. From you. What's that? Just okay. So maybe not this one. NP, and then this is the normal. So let's try this. Okay, so it works. So I'm generating this normal. No, it's not quite. No, maybe let's try not to use this. NP normal doesn't work. NP random, not normal. Huh? Number, random number, random number. No, I am use the random number norm, but just the random number, the random will do. See. And then it should be random. Maybe this should work better. This is what I want. So what I'm saying here is that I am importing the random package. Then I'll call out the random functions from the random package. That would generate me 100 data point. And then after that, I do the binning. So now you look at this binning, not all of them are of equal height. That means there are some number which has a higher probability of occurrence than the other. Okay. It's actually quite complicated. It should be less than 1, but I don't know why is it. Now let's say if you bin it into say this, so this is slightly different. But if you increase the numbers of sample to say 1,000, 100, there are more data point. Maybe I increase the numbers of beans to be say 25 beans. So this is to increase to 25 beans. Let me show where that's what happened. So this is the numbers of beans, the numbers of count without normalization. Okay. So if I increase this to 5,000, it looks like most of these numbers has occurrence, which is more or less the same, right? So if I increase this to not 5,000, say 50,000, then you can take a look at this. So it means that when I generate 1,000 random numbers from this random RAM, it looks like has a equal chance of probability to occur. Now this is just what I mentioned as the this is what I call the uniform distribution. Most of the numbers, well, all the random number has an equal chance of occurrence because the random number generated using this manner is based on a uniform random number. That's generated based on the random, based on the uniform, based on a what I call a random distribution. Now, if I were to the random number, not using a number generator, which is following a uniform distribution. It is okay. So let me check out the help file. So help file on the random. So the help file on random says that this is a random generator. I can use different type of distribution. Right? Uniform is the so when I generate the random number using random.random, this is assuming the default distribution, which is uniform. Okay. but it is possible to have a normal where the number is on the distribution, which is a Gaussian. Let's try to see how you do that. So let me try to generate a Gaussian generator. So this is what Shaz was suggesting. Let me cut and paste from the just now. NP random normal. Maybe let's see how you do that. Random normal. Random. So if I want to get this to be normal, what should I do? Random. So let's see the distribution to be random. Maybe I can try. Maybe it's random.norm. Random. My not very good. Copy and paste. So if you were to use this random np random dot normal, okay, let's try this. So instead of generating the data using random, let me so we generate the random number using the package numpy. So numpy has a random number generator which is of normal distribution. So when I press a button, I'm generating 50,000 numbers where each of these numbers are not distributed uniformly but in a normal distribution. So I expect something which is different. No, this is not quite true. Yeah, I think this is quite true. True, I think this density true is no more. Okay, no. Yeah. So see, maybe not. Now this is the distribution. So I hope that you can see the point I want to make. Now you can always generate different type of distribution, right? So if you just generate random number, range between 0 and 1 using a normal distribution function, then this is the result of the binning. Now this is the result after you have generated 50,000 numbers lying between 0 and 1. No, I think it's lying between 0 and 1. It has a Gaussian distribution which is specified to be, I think, 1 or 2. So the random number generator with a normal has a default assumption on the sigma and mu. Will not be line and 1, but it will lines from some numbers, say I think sigma, a few sigma away on the left of mu and a few sigma away on the right of mu. And then this number would be generated 50,000 of them. So if you bin it into 25 bins, then this is the distribution function that you obtain. But if you were to use it, generate data based on random, then the number that is generated would have a distribution which is uniform. You can see it like this, right? So now you can have different way of generating data, right? You can say generate 1,000 data, but all these numbers of the data has a fair chance or the same chance to be generated. Or you can generate this data in some distribution function. So you specify the function. So if you specify the distribution function, some number would has more chance to be generated as compared to others. For example, this one, right? So in this case, the values of x, which is around 0, it has a more chance to be calculated or be generated compared to values of x, which is far from the mean, right? And this distribution just represents the Gaussian distribution. Okay, so now you can generate data points using different using different distribution functions. So in this particular example, I have only shown you two ways, right? First, you can generate a data point, 50,000 data point using a normal distribution or using a random or using a uniform distribution. Now, in principle, it is possible to use any of these distribution function to generate the data set. We can say, okay, now can you please generate for me 5,000 values, where these 5,000 values of data is generated based on, I'll say, normal distribution. So in that case, you have to specify what is your sigma and mean. We can also ask to generate a data point which follow a binomial distribution. So by specifying what is your values of n and p, right? So what are we going to do next is to try to be more formal. So let us try to generate some distribution function or some data set based on some specified distribution function. And for example, you can use this sample. You can use this command ss slash. This is not slash. This is command. Yeah. So this is the correct command. So what I do is to data point by specifying the distribution function. So in order, we have used a command called res. Res is another function in stats. Now, just now when we generate the PDF, remember we use SciSpy dot stats, right? Then what we are using is a PDF or PNF. Then we specify the name of the PNF. Then we specify size. For example, norm. Then PMF. Then we specify the parameter P1 and P2. So by doing that, this will generate the distribution function for the normal distribution. But in the case where we want to not to generate the distribution function, but to generate the data point instead, we are going to replace the PMF or PDF by SRV. Stand for, I think, your RVS. Sorry, RVS. RVS stand for random variates. Random variates just mean random data or random numbers. And this RVS is just a set of random numbers. So you have to specify the parameters for that particular distribution. So if, for example, if you are generating numbers, random data that obeys a normal distribution, you have to specify the values of mu and sigma for that distribution. You also have to specify how many data points you want. So if you want 1,000, you just 1,000. So that would generate the 1,000 data point for mu and sigma. So let's see if this works. Okay, so let's say mu is 0 and sigma is equal to 1. And then the numbers of data point is 1,000. I think we call this a name called, size. Yeah, we call it size. Sizes mean the numbers. So the size is 1,000. So this is what you do, right? So SciSpy stats the name of the distribution function you want. Then this RVS stands for generating independent data point, where these data points fulfill the normal distribution with mu equals to 0, sigma equals to 1, and 1,000 data points. So when I press the button, now I get nothing. The reason is because I have not defined SciSpy, so import SciSpy. Okay, so that is what I get. So this is a raw data. So this is a set of data point, 10,000 data point, which follow certain type of distribution. So let me try to cut and paste this. This one, this would plot the histogram of the data into 25 bins. So by bringing this in, I'll be able to bin the data into a histogram. That is what you get. Right? So this is the histogram that is meant for the data generated by RES. And this is a data set that follows a normal distribution. So it looks like a normal distribution. Is it like it has a mean 0 and it has a width of roughly 1. Right? So if you make to be say 10, then you expect that the spread will be larger. Here it will be like no, not from 0 to 1, but from 0 to 10. Let's try this and see whether this is true. So when I press this here, you see that the width become larger. Right? But it still doesn't look like it is really a Gaussian distribution. Now, how do you see that it's really a Gaussian? You increase the numbers of data points. The more point you have, then the more is the sample to resembles a true Gaussian distribution function. Okay? So that's how it looks like. Okay, so now, so let us look at the x coordinate and y coordinate of the histogram. So let me try to print this. So the plot is PLT, plot PLT HIST. Let's see what is the size of this. This one is an array, I think. Let me print this. Maybe print this and see what happens. So the output of this is an array. Right? It has an array. The first element of the array is this, and the second element of the array is this, and then this is a part, a patch. So if you check the dimension or the length of this, PLT HIST is an array with 3 elements, and if you print out the first element, you get this array. And what is this array? This array is actually the X bin. Right? This is a bin. Bin means that the values of X first bin, this is the value of the first bin, values of X in the second bin. Let me check, see if this is correct. No, I think this is a histogram. Second values of this is 1. Okay, 1. This is 1. Now, what is this? This looks to me and it is an right. So this refers to the X value of the first bin, and this is the second values of the second bin, values of third bin. So the second component here is the bins, right? So it is the values of the bins, and then this is called a histogram. So I call the first histogram, and I call this bins to be the second component. So I print out the bins. So the bins is just the values of the X value on the X-axis, whereas the histogram is just so it's a value of the height. This is the numbers of counts which is not been normalized yet. So if you want to normalize it, I think here this has to be say density. True. Not sure whether this one works. Yeah, it works. So if you true in plot here, then normalize properly. Okay, so now you see that this is the height, which is referring to a percentage, which is less than 1. So if the truth in this histogram, it's correct. So, but let's just try to see if you can print a plot, the plot of this. Let's just try to see print histogram, the length of the histogram. I just want to show you something. The length of the histogram is 25, whereas the length of the bins is 26. So the histogram is the numbers of column. So like the numbers of histogram is just the numbers of values of the whereas the beans is the values of x at the edge, right? So if you look at this, if you look at this one, for example, you have 1, 2, 3, 4, 5, 6, 9 beans. But how many x value at the edge you have? You have x0, x1, x2, x3, x4, x5, x6, x7, x8, x9. So there are 9 x's, but there are only 8 beans. So this is what is happening here, right? So the numbers of plot, the number his and the numbers of beans are slightly different by 1. Therefore, if you were to say, I want to plot PLT, let's say PLT, plot beans, this is a value, and his, then you have trouble. You would not be able to plot because the dimension of bean and his is not the same. So what you need to do is that you need to take away the beans by 1. So what you do is that you remember these beans. You just say you take the beans. See, let me show you this one. Beans. If you do like this, this will show you all the bean. This will show you all the beans. Right? So this will show you all the values of bean from the beginning until the end. And there are extra 1 number. So what we need to do is I'm going to take this away, the last values away. So I'm going to take until from the beginning to the last. So this will give me only up to 37, where I kick out the last number. So when I do that, this will give me all numbers except 40. Okay? Right, the 40 is done. So I take off one of the values in the bean. I'm going to finish it very soon. Then I'll redefine my beans to be 1 number less. So in that case, the numbers of beans here would become the same as the number of histogram. So let me show you this. I'm going to print out the values of beans. So this will be the x value. I'm going to plot, and then I'm going to this will be the y values. This is h values, and this is the y values. So you can actually combine them, and then you can now plot the beans together with the histogram on the plot. This line comes from this. So maybe I should just put another asterisk. Okay, so points are coming from the plotting of the beans versus histogram, which is on the left hand side of the edge of a bean, and the right hand side, the last bean, this one is been taken off. The values of the x, last x, on the right hand side of the last beans is taken off. So we have now beans tallying with the numbers of histogram value. So now you can see this quite well. Okay. So maybe we don't have much time to continue on this, but at least let me conclude this. It is possible to generate statistics set of data based on a given distribution. So if you want a normal distribution, you just specify the normal distribution. Then you specify the parameters for this normal distribution. If you are generating, for example, a binomial, then you say binom. Then for binomial, then you have to specify that I think the n and then p, specify n and p. Then let's see if I can say this binomial. I call this say n, say 1, and this is called p. Maybe p is a number which is say 0.5 and say 10. So this would generate for me a binomial. I'm not sure whether this is true. Let me check. Binomial. I think I have a code here for binomial. Yeah, NP. Yeah, so NP. So this is the way how I do it. Binomial. Yeah. So it doesn't look very nice for some reason. Can come back to this on. It's not like it is quite true. Maybe n should be larger. Maybe 25. Let's see if it's working. No, it's not working very well. 0. P binomial is say 9. Not 25. P should be. I have to fix this later. But anyway, what I've learned today is that you use the function RVS of any distribution you like. After you have generated data, you can use the histogram to show the histogram of that data. So we learned today. So we're going to stop here for a moment and we'll continue from here onwards in this coming Friday. Now, I suppose that it is quite taxing for you. I have actually prepared an assignment 6.2. You have 1 week to do it, but I don't think that you would want to do it. So this assignment is actually quite a difficult one. So maybe this today we are not going to do the assignment yet. So I'm going to take off the assignment for the moment. But no, sorry. So I'm not going to do the assignment. Where am I? So I'm not asking you to do the assignment today. I'm going to give you more days. Maybe I'll have to delay this one. Now, if you want to try and try, but you don't need to do it. So assume, you can take it as today. You don't have a assignment until next lecture. Okay, this is kind of a difficult assignment. But if you want, you can try to see what kind of assignment is this. It's actually very interesting. It is asking you to generate a chi-square distribution. So if you know how to generate a data, you can generate the chi-square distribution, and then you show that yes, the data that you generated from the chi-square distribution really indeed follow the formula that you expect. Okay, so that's all for today. We're going to finish it maybe this coming Friday. Okay. So any questions before I leave? Any response from you or any questions you want to ask? No. No, I want to ask anything or say anything to me. You can switch on your mic before we end this session. Any feedback that I can respond to you? The notes that I have prepared for you today is kind of a comprehensive. Okay, so I've tried to explain all you need to know in plain text form, and try to run this assignment, run this exercise yourself. Now, if any questions, we can discuss it. Send me any message later on. But hopefully by next lecture, we'll be able to attempt the assignment. Okay. So it's 508. If you finish with this, but then we just stop. Okay, no problem. Okay, so you have to wait for a few days before things can be uploaded online. Okay, we end here.